Viewers, so in this part we are going to be handling physical chemistry, specifically colligative properties. Now this video is presented to you by Ebullioscopy, and you are advised to share the video to your friends, subscribe to the channel and like the video. We're going to be looking at the first part of colligative properties. So this video is going to be split into two. So this is the first portion. We are going to be looking at both the lowering of vapor pressure and the elevation of boiling point. So we are going to be looking at colligative properties, and we are saying that colligative properties are going to be the properties that can be measures over a range of concentrations of the solutions, and the results obtained are going to depend totally on the number of solid particles present in a fixed amount of a solvent. And it's only going to be holding for, or it's going to be valid for dilute solutions. So whenever you are dealing with colligative properties, you should know that these are going to be properties that are dependent on dilute solutions. And also it's only going to be dependent on the number of solid particles that are present in a given solvent. So how can colligative properties be defined? So we are going to define colligative properties as the physical properties of a dilute solution which only depend on the number of the non-volatile solid particles present in that solution, but they are independent of their chemical nature of the solid particles. So whenever defining this definition, what you shouldn't leave out, we need to see that they are physical properties, and the other thing is we need to see a dilute solution. The other thing is the solid must be non-volatile, and also the solution should be independent of the chemical nature of that solid that has been dissolved in it. So we are saying that the greater the number of particles in a solution, the greater the extent to which the colligative property is affected. Now, what are the sum of the colligative properties under physical chemistry? So for the colligative properties, you are going to look at Roman number 1, or number 1, to be having lowering of the vapor pressure of the solvent. And number 2, we are going to be looking at elevation of the boiling point of the solvent, and also freezing point depression of the solvent or solution. And lastly, we are going to be looking at the osmotic pressure of the solution. Now we are saying that colligative properties are important in such a way that they are going to enable us to determine the molecular masses for the non-volatile solid particles that have been dissolved in them. Downsides of the colligative properties, or what are the limitations or the rules that govern colligative properties. So we are saying that limitation number 1 is going to be that the solid that must be dissolved should not associate or dissociate in solution. Now associating means that particles in the solution, the solid particles in the solution, come together or react to form a compound. But dissociation means a compound splits to form either ions or more solid particles. That's why I gave one example here for dissociation. Now I say that when solid particles dissociate in the solution, the number of particles in the solution is going to increase, because look here, 1 mole of sodium chloride is dissociating to give us 2 moles of ions of sodium ion and chloride ion. Now we are saying that, if the number of particles in the solution increases, the value of the colligative property is also going to increase, but in turn is going to reduce the relative molecular mass. So that means that relative molecular mass is inversely proportional to the value of the colligative property, or relative formula mass is inversely proportional to colligative property. The higher the value of colligative property, the lower the molecular mass. And the higher the molecular mass, the lower the value of colligative property. So that's what we mean by inversely proportional. So we are saying that the molecular mass is obtained by colligative property for a solid that dissociates in solution is therefore going to give us a lower value, because for dissociation we are increasing the number of particles in the solution. Now, once we increase the number of particles in the solution, we are going to be increasing the value of the colligative property. The more we increase the value of the colligative property, since colligative property is inversely proportional to relative molecular mass lowers. So the higher the value of colligative property, the lower the relative molecular mass. And the lower the value of colligative property, the higher the relative molecular mass. So number 2, we are saying that the solution must be dilute, or the solution is dilute. And number 3, now these are general limitations that should be applied anywhere in any of the colligative properties that you are going to be looking at. So number 3, there should be no chemical reaction between the solute and the solvent. And number 4, the solute should be non-volatile. Now let's look at colligative property 1 as stated above. So you're going to be looking at vapor pressure lowering. Now what is vapor pressure of any liquid? Vapor pressure of any liquid is going to be the pressure the pressure of the vapor, any liquid, the vapor pressure of a liquid is going to be the pressure exerted by the vapor when it is in equilibrium with its own liquid at a given temperature. So whenever you're heating, say a liquid, the vapor that comes out of that liquid, we are measuring the extent of the pressure exerted by that vapor to be the vapor pressure of that liquid. So you're saying that the vapor pressure of a liquid is the pressure exerted by the vapor when it is in equilibrium with the liquid at a given temperature. So we are saying that the vapor pressure of a solvent in solution is always less than the vapor pressure of the pure solvent at the same temperature. Now, why is this the case? Now, if you dissolve anything in a solvent, you are going to see that the solid particles of that solid that you have dissolved in this solvent, they are going to occupy part of the surface of the solution or the solvent. Now, once they occupy part of the surface of the solvent, it's going to inhibit the liquid molecules from the solvent to evaporate into vapor phase. Now, once they do so, we are going to reduce the pressure exerted by the vapor that is coming out of the liquid. So that means that we are going to increase more heat so that we can give off a more vapor that can give off a higher vapor pressure. That means that whenever you're dissolving anything like another solute into a solvent, it's going to occupy the upper surface of this solvent, and it is going to inhibit the vapor molecules to escape into vapor phase. Now we are saying that this is because the non-volatile solid particles are going to occupy some of the surface of the solution. Now once they occupy some of the surface of the solution, it reduces the escaping tendency of the solvent molecules into vapor phase. Now once the escaping tendency is reduced, obviously the pressure is going to lower because the vapor that is being released is not enough. Continuing, we are telling you that the solution there has a lower vapor pressure than that would be exerted by the pure solvent. You are given a simple question here, and we have told you that explain why an aqueous solution of glucose has a lower vapor pressure than water at a given temperature. Now, aqueous solution of glucose, we are telling you that we got water and we added glucose. So here, glucose is acting as our non-volatile solute, and water is going to be our pure solvent. So the reason remains the same. First of all, you have to tell us that glucose is a non-volatile solute. So once we add the non-volatile solute to a solvent, we are saying that the glucose particles are going to occupy some of the part of the surface of the solution, and it's going to reduce the escaping tendency of the solvent molecules into vapor phase. And once that happens, the solution is going to have a lower vapor pressure than that would be exerted by the pure water, which lacks glucose. So let me hope that is very simple to understand. Now we are saying that for a solvent in solution, the vapor pressure lowering change in P is given by Vapor pressure lowering change in P is given by vapor pressure exerted by pure solvent, Uace vapor pressure exerted by the solution. Because we expect the solvent to exert a larger pressure than the solution. That's why we say that P of the solvent minus P of the solution. Now you're saying that where P of the solvent is going to be vapor pressure of the pure solvent, and P of the solution is going to be vapor pressure of the solvent in solution. So how are we going to find our vapor pressure then? Now vapor pressure in colligative properties, we are going to be using this formula. Change in P divided by the vapor pressure exerted by the solvent should be equal to mole fraction of the solute divided by mole fraction of the solvent. Now how do you get mole fraction of a solid? Mole fraction of a solid is got by getting the given mass divided by its molar mass. Then we divide it with mole fraction of the solvent, which is got by given mass of the solvent times molecular mass divided by molecular mass of the solvent. Before we approach calculations, we have what we call laws governing vapor pressure lowering, and this is going to be called Raoult's law. Now there are two laws for Raoult. Raoult has this law for vapor pressure lowering and the law of physical equilibria. However, whenever we are asking in papers, we are always interested in the one for physical equilibria. The one for vapor pressure lowering is always specified when being asked for. So we shall be asking you to state the Raoult's law of vapor pressure lowering. Other than that, you are supposed to present the one for physical chemistry or physical equilibria. So we are saying that Raoult's law of vapor pressure lowering states that the relative lowering of the vapor pressure of a solvent or a solution containing a non-volatile solute is going to be equal to the mole fraction of the solute in the solution at that very temperature. Now, what are the assumptions or limitations of vapor pressure lowering that are going to be involved? As limitations or assumptions are going to remain the same, just like we looked at in the first slide or in the first session of this video. The solid must always not associate or dissociate in solution. So that should be number 1. Number 2, the solution should always be dilute. And then number 3, there should be no chemical reaction between the solute and the solvent. And number 4, the solute must be non-volatile. Now let's look at the calculations that are going to involve vapor pressure lowering. Now saying that number 1, the vapor pressure of the pure solvent, P0, of ethane at a certain temperature is going to be 32.67 kilopascals. Calculate the vapor pressure of a 3% solution of camphor in ethoxyethane at the same temperature. Now let's see how you're going to overcome that. Now this one is a common term and we use it mostly to trick students. So let's look at what that means. That 3% is going to mean that the solution you are dealing with is containing 3 grams of a certain solute, and the other mass of the solution is going to be 100, the total. So that's why you're saying that mass of the solute therefore is going to be equal to 3 grams, and the solution is going to contain a total of 100 grams. Now, since we know the mass of the solute in that solution, we can get the mass of the solvent because the total solution is containing 100 grams. So to get mass of the solvent, we get 100 less the mass of the solute, and we are going to end up with 97 grams. So molar mass of our solute, which is going to be ethoxyethane, is going to be equal to. Now, you have to show the calculations for getting each and every component. Like here, for carbon, you're having 4 carbon atoms. So 4 times 12, you're going to get 48, which you're supposed to show. You're supposed to show us that you're multiplying 4 times 12. And then if you look at hydrogen, you're having 10. So it's going to be 1 times 10 to get 10. If you look at oxygen, you're having one atom. So it's going to be 1 times 16 to get 16. And the total mass or total molar mass is going to be equal to 74 grams. And molar mass of camphor is going to be given by we're having 10 carbon atoms, so it's going to be 10 times 12 to get you 120. We're having 16 hydrogen atoms, so it's going to be 1 times 16 to get you 16. And we're having 1 oxygen atom, it's going to be 1 times 16 to get you 152 grams. Now we don't know the vapor pressure of the solution, but we know the vapor pressure of the solvent, and the question wanted the vapor pressure of the solution. So we got our formula, which is change in vapor pressure divided by vapor pressure of the solvent should be equal to the mole fraction of the solute divided by mole fraction of the solvent. And I told you, mole fraction of the solute is the same as given mass divided by RFM of that particular component. So that's why I repeated the formula here. So the given mass, we had 3. We divide it by its RFM, which is 152. Now the mass of the solvent was 97, divided by its RFM, which was 74. Now here we do the math, and we simplify, we are going to come up with this. I mean, you find reciprocal. You find reciprocal and you make everything linear. Now here we cross multiply. Now in cross multiplying, this one is going to go this side. And you make sure that everything is done at once. Now if it goes that side, you are going to remain with 0.4919. So since this is negative, we are going to bring P this side, and then we take the product this side. So it's going to be 32 minus 67, and you are going to end up with 32.178 kilopascals. Now let's look at number 2. Number 2 has been prompted you to define the relative lowering of vapor pressure of a solvent, which you defined earlier. And then part B, Roman number 1, at 50 degrees Celsius, an aqueous solution of carbamide of concentration 60.93 grams per decimeter cubed has a vapor pressure of 100 nanometer per square. Now we are being prompted to determine the vapor pressure of water at that very temperature. And number 2, you are prompted to state the assumptions you have made in B, Roman number 1. The relative lowering, definition of relative lowering of the vapor pressure is going to be the difference. Now this is the relative lowering, this is called the relative lowering, this numerator here is called the relative lowering of vapor pressure. So we are saying that relative lowering of vapor pressure is the difference of the vapor pressure of a pure solvent and the vapor pressure of the solvent above its solution with a non-volatile solid divided by the non-volatile solid divided, this is supposed to be solid, non-solvent, divided by the vapor pressure of the pure solvent. Now if you look at part B, if you have to summarize all the data given, vapor pressure of the solution is going to be equal to 12,100. Vapor pressure mass of the solution is going to be 1000 grams, and mass of the solid, it was given to be 60.93 grams. Now you're going to get mass of the solvent. Since you have total mass of the solution, we get mass of the solvent by getting the difference between mass of the solution, which is 1000, you less 60.93, and then you're going to end up with 99.07 grams. Now molar mass of the given compound is going to be 12 times 2 because you're having 2 carbon atoms, and then you're going to end up with 24. For hydrogen, it's going to be 5 times 1, you're going to end up with 5. And then for oxygen, it's going to be 1 times 16, you're going to end up with 16. And for nitrogen, it's going to be 1 times 14, you're going to end up with 14. So this RFM is going to give us, molar mass is going to be 59 grams. Now to get molar mass of water, it's going to be 2 times 1 for hydrogen to get you 2. And then 1 times 16 to get you 16. So molar mass of water, you're going to end up with 18 grams. Now you call the formula you're going to be using this one. So the vapor pressure lowering, change in P divided by vapor pressure of the solvent is equal to mole fraction of the solute divided by mole fraction of the solvent. How do you get mole fraction of the solute? Given mass divided by RFM. So it's going to be 60.93 divided by 59. Everything is going to be divided by RFM of the solvent. How do you get mole fraction of the solvent? It's got by given mass, which is 939.07 divided by RFM, which is 18. Now simplifying, you find reciprocal and you end up with this. Now after that, you are going to cross multiply. After that, you are going to cross multiply and then simplify. So here, you're going to cross multiply and simplify. After you're going to multiply all these. If I'm trying to simplify it for you here, you're going to multiply all these and then you cross multiply this vapor pressure of water this side. After that, you take this on this side and you bring that thing containing vapor pressure of water this side, and then you prime factorize out vapor pressure of water. So you're going to see that you're going to be having, you prime factorize out vapor pressure of water and you divide through by the coefficient. So you're going to end up with 123.44.356 nanometers squared. So if you look at Roman number 2, where they ask for conditions or limitations or assumptions, so these ones are always going to remain the same. The solution is must be dilute. The solid should not associate or dissociate in solution. Always when the solid is given, make sure that you specify the solute. There should be no chemical reaction between the solute and the solvent. And also the salt should be non-volatile. And density of the solution is assumed to be the same as density of water, which is 1 gram per centimeter cubed. If you are to look at number 3, you are being prompted to calculate the vapor pressure. Now you are given the vapor pressure of pure benzene to be 640 millimeters of mercury, and the non-volatile non-electrolyte solute is having a given mass of 2.17 grams. And is added to the solvent benzene with a mass of 39 grams. Now I've been told that the vapor pressure of a solution of benzene is 600 millimeters of mercury. Now calculate the molar mass of the solid substance. Now if you are to summarize out the data given, vapor pressure of the solvent has been given as 650 millimeters of mercury. Vapor pressure of the solution has been given as 600 millimeters of mercury. Now mass of solid given is 2.175 grams, and mass of the solvent that was given is 39 grams. So to get mole fraction, remember that we have to get molar mass. So we get molar mass of both the solute and the solvent. Now the solvent was benzene, and benzene is given by this formula. So its RFM is going to be got by 6 times 12 plus 6 times 1. So if there was supposed to be 6 times 1 around here for hydrogen. So you are going to end up with 78 grams as the molar mass for our solvent, which is benzene. Now molar mass for the solute was unknown, and that's what you are being prompted to calculate the molar mass of the solid substance, which was the solute. So as given by the formula, change in vapor pressure of the solution divided by the vapor pressure of the solvent should be equal to the mole fraction of the solute, which we get by given mass divided by RFM divided by molar mass of the divided by mole fraction of the solvent, which you also get by given mass divided by molar mass, its molar mass. So substituting, this is going to be 640 less 600 divided by 640 is going to be equal to this. Now we find reciprocal this side so that we can make everything linear, and then you cross multiply. Now cross multiplying, 640 is going to come in the numerator. Now this one is going to come here and 40 is going to come here, so they change position. That's why you're having 2.175 times 78 times 640 divided by 49 times this 40, which was up here. So simplifying using your calculator, you're going to end up with 69.6 as the molar mass of the solute that was required. If you look at number 3, if you are to start to extract out data right away, the vapor pressure of carbon disulfide at a certain temperature is 400 millimeters of mercury. So carbon disulfide is going to be our solvent in this case. So that's why vapor pressure of the solvent. So you start by extracting out data. Vapor pressure of the solvent is equal to 400 millimeters of mercury. Now you are being told that at the same temperature, a solution of 5 grams of sulfur. Now this means that this is the mass of the solid. That's why it's written here, mass of the solid is equal to 5 grams. So that's how you extract out data. Now it was given in 63 centimeters cubed of carbon disulfide has a vapor pressure of this. So vapor pressure of our solution, because they talked about solution here, vapor pressure of the solution is this: 392.58 millimeters of mercury. Now we are telling you that if the density of carbon disulfide is 1.27 gram per centimeters cubed, Roman number 1, you are prompted to calculate the relative molecular mass of sulfur. Now, since we have to get molar fractions, we have to get the molar masses of either of the components present. So molar mass of carbon disulfide, which is given by this formula, is going to be equal to 12 times 1 plus 2 times 32 to give you 64. And this is going to end up with 76 grams. Now, mass of the solvent. How are we going to get mass of our solvent? Now, to get mass of our solvent, you are being given volume. You are being given volumes and density. Now, to get mass of anything, you get its volume multiplied by density. So that's why we are saying that to get mass of any solvent, you get its volume, which is 63, multiplied by its density, which is 1.27, and you're going to end up with 80.01 grams. So this is going to end up to be your mass of the solvent. To get any mass of anything, you get a given volume multiplied by its density. That's how you get mass of components. And you are going to be using that idea everywhere, even in thermochemistry. Now, we don't know the molar mass of sulfur, and it was the one which was required. So the first things first, you call the formula. Formula is given by changing P divided by vapor pressure of pure solvent divided by, should be equal to mole fraction of the solid divided by mole fraction of the solvent. And I've already told you get mole fraction by getting given mass divided by the RFM. Now substituting, you're going to have 400 less 392.58 divided by 400 should be equal to 5 divided by molar mass of the solute divided by 80.01, which is going to be divided by 76. Now notice that each of these is mole fraction, and we get mole fraction by getting given mass divided by the RFM. Now you find reciprocal this side, you're going to end up with 5 times 44 divided by molar mass of the solid times 80.01. Now this one goes up here, we cross multiply it back, and this one we cross multiply it this side. Now this one drops here, and then you end up with 400 multiplied by 5 multiplied by 76 divided by 7.42 multiplied by 80.01. So you're going to end up with your molar mass of the solid being equal to 256 grams. Now if you look at part B, they told you to deduce the molecular formula of sulfur in carbon disulfide. Now all of you know that sulfur is written in any molecule is written in. For any molecule, it's written in a given formula, and we attach it to any value of n, and we equate it to the calculated molecular mass. So sulfur is going to be 32. 32 times 1 is going to be 32. Then multiplied by the n, you are going to end up with 32n, and you equate it to the mass you have got. And then you divide through everything by 32 to get n as 8. So it means that the molecular formula of sulfur, therefore, is going to be S8. That means that sulfur is tetraatomic. Now, if you look at the vapor pressure of water, if you have to summarize all this question, they tell you that vapor pressure of water is 23.7 millimeters of mercury. So that means that vapor pressure of a solvent is equal to 23.7 millimeters of mercury. Now they tell you that this is at a certain temperature. Now calculate the lowering in vapor pressure that occurs when 12 grams of urea. Now this obviously is going to be the mass of the solid. Once you read out something, you summarize it out. Mass of the solid is equal to 12 grams. Now you're being told that to calculate the lowering vapor pressure, and lowering vapor pressure of told is given by changing P, which is always the numerator on the left hand side, are dissolved in 1 liter of water at the same temperature. Now since we have to get mole fraction, you always have to get RFM for the solid, because the formula was given. So this is going to be, now we had 2 nitrogen atoms, it's going to be 2 times 14 to get you 28. We had 4 hydrogen atoms, it's going to be 4 times 1 to get you 4. Now we had 1 carbon atom, it's going to be 1 times 12 to get you 12. and we had one oxygen atom, it's going to be 1 times 16 to get you 16. Now calculating all that, you're going to end up with 60 grams as your molar mass for the solute. Then what about the solvent? Remember that the solvent we're using water, and water has a standard formula, which is H2O. So to get molar mass of water, you have to show the calculation. So it's going to be 2 times 1 plus 1 times 16 to get you 18 grams. Now to remember, I told you they're asking for calculate the lowering in vapor pressure, and lowering in vapor pressure I told you is the denominator, is the numerator on the left hand side. So that's why we are presenting it with change in P. So change in P divided by vapor pressure of a pure solvent should be equal to the mole fraction of the solute divided by its molar mass. Now everything is going to be divided by the mole fraction of the solvent. Now to get mole fraction of the solute, the given mass was 12 divided by the RFM, which is 60. For the solvent, the given mass was 1000 because they gave us 1 liter of water. Now I told you to get the volume of anything, you get its volume multiplied by its density. We all know that the density of water is 1 gram per centimeter cubed. So how are we going to get the given mass of water? So since the volume was 1 liter and the density of water is 1 gram per centimeter cubed, we get 1000. We multiply it with 1000 with 1 and we get 1000 grams. So the meaning of that is now clear. So given mass was 1000 divided by RFM, which is 18. Now you cross multiply and you make change in P the subject. You find reciprocal here to go here. Now you make change in P the subject and you substitute everything in the calculator. You're going to end up with 0.08532 millimeters of mercury. So if you look at number 5, you are being given that the solution contains 4.45 grams of a solid X and it has been dissolved in 1 kilogram of carbon disulfide. Now that means that the given mass of the solid given is 4.45 grams and mass of the solvent is equal to 1 kilogram, which is the same as 1000 grams, because when you're calculating, everything must be in terms of grams. Now you're also being told that another solution contains 6.42 grams of sulfur. Now that's for another solution, and that's for part B. Now you're being told that in the same mass of carbon disulfide. Now if there are two solutions have the same vapor pressures at the same temperature, calculate the relative varying of vapor pressure. Now if you are to consider for part A, if you are to consider for a solution of X in carbon disulfide, now we don't have vapor pressure of the solvent. Now that's what they want you to calculate the vapor pressure lowering, which is given by change in P. Relative lowering of vapor pressure, change in P, which is the same as vapor pressure of the solvent minus vapor pressure of the solution. Now also, you don't have vapor pressure of the solution. So we are being told that molar mass of X, you are being given here in the question that molar mass of X is equal to 178 grams. And molar mass of our solvent is going to be calculated because we know the formula or the molecular formula of carbon disulfide, which is going to be 12 times 1 because carbon atom is 1 plus 2 times 32, which is 64. Now once you add up the 2, you're going to end up with 76 grams. Now we always use this formula for lowering of vapor pressure. Change relative lowering in vapor pressure divided by vapor pressure of the solvent should be equal to the mole fraction of the solute divided by mole fraction of the solvent. Now here, to get mole fraction of the solute, you get given mass divided by RFM and then divided by molar mass of the solvent, which is also given by given mass divided by RFM. So you find the reciprocal this side and you end up with this. So you leave this expression unsimplified and you simplify this, and if you simplify it, you're going to get 0.019. Now if you are to look at for a solution of sulfur in carbon disulfide, if you look at a solution of sulfur and carbon disulfide, you are going to also consider some data. Now you have to recalculate the value of the RFM because these marks are distributed equally. So you recall the same formula that change in vapor pressure divided by the vapor pressure of the solvent should be equal to mole fraction of the solid divided by mole fraction of the solvent. Now you should be asking, why aren't we handling this part? Now the reason why you're not handling this part is because you are told that they have the same, you are told that in the question, if the two solutions have the same vapor pressure at the same temperature. So if they have the same vapor pressure at the same temperature, that means that we can leave this out and we just simplify this side, and then we equate this side to this. Let me hope that is very clear to understand. So that's why we are not tampering with any of these sides. So doing so, mole fraction of the solid is given by this, mole fraction of the solvent is given by this. Just have been explaining. You find reciprocal and you try to simplify this. Now since these two solutions have the same vapor pressures, we are going to equate this one to this. In part B, since the two solutions are having the same vapor pressures and they are of the same solvent, that means that we are going to equate the expression you have got in the second calculation, we equate it to the expression we got in the first calculation. And once you do so, you only need to make molecular mass of the solid the subject by bringing this one this side and you take this one this side up. So you're going to have 6.42 multiplied by 76 divided by 1000 multiplied by 0.0019 to give you 256.8 grams. So saying to get molecular formula of any compound they told you, you always multiply by n. So it's going to be 1 times 32n, which is going to be 32n to be equated to 256. Now you're going to get your value of n as 8. So that means that sulfur is always tetratomic, and this structure is always given by this. I hope you looked at this in your physical chemistry under structure and bonding. So that's how sulfur exists, and you must know this structure as a must because it's highly examinable. The graphical representation of the vapor pressure lowering. Now for us to represent when sometimes you are being given graphs and you are after being given that graph, you are being prompted to calculate the RFM or the molecular mass of the solvent or the solute from that graph. So how do you come over that? So I'm just going to pass through this just to guide you on what you're supposed to do. Now you're always going to find, you are supposed to find the change or the relative value in vapor pressure. In the question, they don't give you the change in P. You are supposed to do it yourself. So you're saying that a graph of low and low vapor pressure is being equal to that pressure of the solvent, you less vapor pressure of the solution. Now you're saying that again it's mass of a solid, which is a straight line through the origin. Now you are supposed to get the slope. After getting the slope, you are supposed to equate it to the, after getting slope, you are supposed to equate it to this, which is molar mass of the solvent multiplied by its vapor pressure, and it's going to be divided by molar mass of the solid times the given mass of the solvent in the question. So you must understand and always remember this formula. So I hope everyone is well conversant with finding slope. That's why I'm not emphasizing it more. Yeah, it's the same idea, but this side you're saying that it's a graph of lowering of vapor pressure, and I've told you lowering of vapor pressure is indicated by changing P, which is got by vapor pressure of the pure solvent. Now, how are you going to realize that vapor pressure of a pure solvent? This is always the first value that is going to be given in your table when the question has been given. They tell you that mass of the solid dissolved, and they are going to say mass of the solid dissolved at that point is 0. Once mass of the solid dissolved at that point is 0, then you should consider that vapor pressure to be the vapor pressure of the solvent. It's as simple as that. So the less the vapor pressure of the solution. Now we are saying that again it's the concentration, which is going to be measured in mole per decimeters cubed of a solid in a solvent, and it's going to give a straight line passing through the origin as represented in this sketch. Now we are saying that the slope of the graph is going to give the value molar mass of the solvent multiplied by its vapor pressure, the vapor pressure it exerts in its pure state, divided by density of the solvent times 1000. So this is an alternative formula for finding for finding any of the things that you are going to be asked, especially molar mass for the solvent. So you can find it from the slope. Now I noted here, because I know some of you may forget, that the data you are usually given may require you to change the relative lowering vapor pressure first before plotting the graph. Now you're saying that vapor pressure of pure solvent is the vapor pressure when the concentration is equal to 0. That means the concentration of the solution is 0. That means that the vapor pressure of the solvent is going to be greater at that point. Now each P of the solution value is subtracted from the P of the solvent value to get change in P values at the different concentration values. Let's look at the elevation of boiling point. Now we are saying that boiling point of a liquid, for a definition, is going to be the constant temperature. Now this word is very vital. Without this you can't get anything. Boiling point is going to be the constant temperature at which its saturated vapor becomes equal or gets into equilibrium with the external pressure that is present on the liquid. Now you're saying that the vapor pressure of a liquid decreases when the non-volatile solid is dissolved, just like explained previously in it. Now you're saying that the decreased vapor pressure implies that for any solution to boil, it must be heated to a higher temperature than its partial boiling point, so that equilibrium between vapor and the external atmospheric pressure can be attained for boiling to take place. Now we are saying that pure water boils at 100 degrees Celsius and an aqueous solution of sodium chloride boils at 106 degrees Celsius. Now explain why. Now remember that when you are beginning this video, I told you that sodium chloride undergoes dissociation, and once it undergoes dissociation, it forms two ions, or it increases the number of non-volatile solid particles present in the solution. Now these particles are going to occupy part of the surface of the solution, and it's going to inhibit the escaping tendency of the liquid molecules or solvent molecules to vapor phase. So that means that for the liquid's vapor to get into equilibrium with the external atmospheric pressure, more heat must be required to heat so that more vapor molecules can leave the solution or solvent, which is going to waste more energy. So let's look at the reason. We are saying that sodium chloride is a non-volatile solid. When dissolved in water, sodium chloride particles are going to occupy some of the surface of this solution, which in turn is going to reduce the escaping tendency of these solvent particles into vapor phase. Now you see that the solution there has a lower vapor pressure than that would be exerted by pure water. Now you're saying that the solution should therefore be heated at a higher temperature than that of its boiling point, so that equilibrium between the vapor pressure of its solution becomes equal to that of the atmospheric pressure for boiling to take place. Remember that for boiling to take place, equilibrium must be created between the vapor exerted by the solvent with that from the atmospheric pressure. But remember that the pressure exerted by the vapor of the solvent is going to be reduced by the sum of the particles of sodium chloride present on the surface. So to increase the pressure, we have to increase the amount of vapor coming out of that liquid. And we are going to do so by increasing temperature. So that's why we call it elevation of boiling point. We have to heat the liquid beyond its boiling point temperature. So that's the reason why we name it elevation of boiling point. Let's look at the vapor pressure temperature diagrams under Ebullioscopy. Now you're saying that you're going to plot a graph of vapor pressure measured in millimeters of mercury against temperature, which is measured in degrees Celsius. Now we are having two curves. We are having curve AC and you're also having curve DE. Now how are we going to describe these curves? Now we are saying that curve ABC, remember that this is, for boiling point, you are going to be lowering vapor pressure. So that means that the higher the vapor, the one with the highest vapor pressure is going to be the curve for the solvent. Always remember this. Whenever we are adding a non-volatile solute, it's going to lower vapor pressure. So that means that the curve that is up is going to be for a pure solvent, and the curve that is down is going to be for a solution where non-volatile solutes are present, because they are the ones that are going to lower vapor pressure. Now you're saying that curve ABC represents variation of vapor pressure of pure solvent with temperature. Now you're saying that curve DEF is going to represent the variation of vapor pressure of the solution with temperature, just like I explained. Now you're saying that curve DEF is below curve ABC at all temperatures because the vapor pressure of the solution is always being lowered than that of the pure solvent. And the reason for that is because for the solution, we are having non-volatile solid particles that are occupying part of the surface of the solution. Now, once they occupy part of the surface of this solution, it reduces the escaping tendency of solvent molecules into vapor phase, hence reducing the pressure exerted by the vapor above that solution or solvent. Now, you're saying that T0B is going to be the boiling point of pure solvent, TB is going to be the boiling point of the solution. And to get the elevation, now changing the boiling point elevation, as you are hearing elevation, that means that the solution is going to have a higher boiling point compared to the solvent. So to get the boiling point elevation, we are going to say that it's going to be boiling point of the solution less the boiling point of the pure solvent. So we're saying that the greater the concentration of the solid particles in the solution, the greater the boiling point elevation, because that means that we have to heat that component or solution the more so that we can exert a vapor pressure that can counterbalance the atmospheric pressure for boiling to take place. That's why it's called boiling point elevation. And we're saying that therefore a curve of more concentrated solution will be below curve DEF. The more concentrated it is, the more the vapor pressure is lowered. So the one at the top is always for the pure solvent, the ones down are for solutions. Look at the Ebullioscopic constant. Now we are saying that the boiling point constant for the solvent, or the molar boiling point constant, is represented by K, which is capital, and a subscript B. Now we are saying that the definition of the Ebullioscopic constant can be defined as the elevation in the boiling point caused when 1 mole of a non-ionizing or non-volatile solute is being dissolved in 1,000 grams of a solvent. So you should always remember this, because we always ask this one. Elevation in boiling point caused when 1 mole of a non-volatile solute is dissolved in 1,000 grams of a solvent. Now let's look at the experimental determination of the molecular mass of any substance using the boiling point elevation. Now here you are going to be using Cottrell's apparatus to find the relative molecular mass of the benzoic acid as the non-volatile solute that's going to be dissolved in our solvent, that's going to be propanone. Now for any experiment in physical chemistry, I always advise you to first master the diagram, because it's the diagram that is going to help you remember most of the procedures that you're supposed to present. And if you look at this diagram, you are seeing that you're having a glass tube containing a side arm, and that side arm is going to the condenser, and you're also having our Beckman's thermometer, which is connected to the Cottrell's pump. Now this is going to be the inner tube that's going to control the temperature, and you don't have an STR anywhere, so it's going to be a wide tube. In most cases we use a glass tube, so it can be either solvent or a solution. You put one, don't put all of them. And this is going to be a platinum wire that's going to be used in heating. So let's look at the procedures. Number one, we are saying that a known mass of pure propanone. Now remember that propanone is our solvent. So this side we used a given example. In the questions that you are going to be asked, you are also supposed to specify that solvent. The solvent comes first. a known mass of a pure solvent, we specify it as X gram. It's going to be placed in a wide glass tube, a wide tube fitted with a side arm, just like we saw in the diagram. Like I've told you, to master experiments very well, you must first make sure that you have mastered the diagram, because the diagram is going to give you what you're going to be writing down here, leading to a reflux condenser. Now you're seeing that the boiling tube is then going to be closed and it's going to be stoppered. By a stopper through which is going to be passed a second inner tube, and this second inner tube is going to be fitted with our Beckman's thermometer. Now, I've seen that in the liquid, a collateral pump is going to be inserted, and this is going to be used to prevent superheating. Because here, we are going to be involving heating, and we are going to be using platinum wire. So that's why that platinum wire is surrounded by a collateral pump, and the purpose for a collateral pump is going to prevent superheating. For every point you give out in chemistry, make sure that you give out a reason attached to it. Now we are seeing that the propanone is then heated until the Beckman's thermometer shows a constant temperature, and that's going to be noted as T0B, at which the boiling is going to start to occur. Now we are saying that a known mass, remember that when we are defining boiling point of any component, we told you that it's a constant temperature at which the vapor of the liquid gets in equilibrium with its own liquid. So also here, you are supposed to tell us that the Beckman's thermometer must show a constant temperature, because the boiling is going to take place at a constant temperature. Now we are saying that a known mass of benzoic acid Y grams, now this is our solid, is going to be added using from the side arm, and it's going to be added to the solvent. Now the solution is going to be heated again until the Beckman's thermometer shows a constant temperature at which it's going to start to boil, and this is going to be noted as TB degrees Celsius. Now let's go on to the treatment of results. Mass of the solvent we used is X grams. Mass of the salt we used is Y grams. Now we are going to take the boiling point elevation constant, or Ebullioscopy constant, to be Kb, which is the denotation constant, degrees Celsius per mole per kilograms. Now elevation boiling point, obviously we get that one for the solution, we less that one for the pure solvent, and everything must be in terms of degrees Celsius. Now you're going to say that X grams of propanone dissolves Y grams of benzoic acid. Now always, this is the first statement. You always start with the solvent, and then this side, on the left hand side there must be the solvent, on the right hand side there must be the solute. So X gram of a solvent dissolves Y gram of a solute. Then what about 1000 grams? So 1000 grams will dissolve what? It's going to be 1000 multiplied by Y according to the quantitative chemistry knowledge. 1000 multiplied by Y divided by X, grams of benzoic acid. And contain that. Now the mass you get in 1000 grams is going to be the elevation that is going to be caused by the elevation that was caused in boiling point. So that's why we're saying that change in elevation of boiling point is going to be caused by that mass, which was 1000 multiplied by Y divided by X, grams of benzoic acid. But remember that we're interested more in the molar mass, and the molar mass must be in terms of Ebullioscopic constant. So if the elevation boiling point caused that mass, then what about our Ebullioscopic constant? Remember that Ebullioscopic constant is in terms of 1 mole, and 1 mole represents the RFM of any compound or substance. So that's why after saying that changing elevation of boiling point is caused by this mass, then what about our Ebullioscopic constant is going to cause which change or which elevation? So Ebullioscopic constant Kb is going to cause an elevation of 1000 multiplied by Y multiplied by Kb divided by X times change in T, grams. And then thereafter, since Kb is in terms of 1 mole, that means that every mass is going to give us this side is the molecular mass. That's why we conclude and we say that, therefore, the relative molecular mass of benzoic acid is going to be given by this. Now, what are the assumptions or limitations for boiling point elevation for determining relative molecular mass? Now, I told you these assumptions are always going to remain the same. The solid should not dissociate or associate in solution. The solution should always be dilute, and there should always be no chemical reaction between the solute and the solvent. And lastly, the solute should be non-volatile. Now, what if the solute is non-volatile? Or what if the solute associates or dissociates? For example, look at this question. We told you that explain. Now remember, I told you the higher the value of the colligative, the higher the number of solid particles in the solution, the higher the value of colligative properties affected. And I also told you that the higher the value of colligative property, the lower the relative molecular mass. And the lower the value of colligative property, the higher the relative molecular mass. That means that colligative property is inversely proportional to relative molecular mass. Now we are saying that explain why the molecular mass of ethanoic acid obtained by Ebullioscopic method is 120 grams using benzene as a solvent. Now, since we don't know we have to calculate the theoretical molecular mass for methanoic acid, which is going to be given by 2, since we're having 2 carbon atoms. 2 times 12 is going to give you 24. Then 2 times 16, because you're having 2 oxygen atoms, is going to give you 32. Then plus 4, because you're having 4 hydrogen atoms times 1. And the total RFM is going to be 60. So if you look at this, the given mass in the question is twice the actual theoretical value. So what comes with that? I told you that if colligative property is higher, molecular mass is going to be lower. But in this case, in the question, molecular mass is higher. That means that the value of colligative property was low. And also it means that number of solid particles in the solution reduced. So what brought that? We are saying that the molecular mass of ethanoic acid obtained by boiling point elevation is twice the actual value. Why is this the case? This is because the solid is going to associate through intermolecular hydrogen bonds. Now, intermolecular hydrogen bonds are going to be the bonds formed between oxygen and hydrogen between different molecules of ethanoic acid. That's what we call intermolecular hydrogen bonds. And once we are forming those intermolecular hydrogen bonds, we form dimers. That means that if 2 molecules of ethanoic acid combine, we are reducing the number of solid particles by a half. And that means that also when we reduce the number of solid particles, also the value of colligative property reduces. And once the value of colligative property reduces, the value of the relative molecular mass increases. Now we are saying that the number of ethanoic acid molecules in benzene solution is therefore the half of the original number of the initial molecules that must be present in that pure solution. This is supposed to be solution. Now we are saying that this lowers the boiling point and increases the relative molecular mass to twice the actual value, because I told you lowering the colligative property, which in this case is the boiling point elevation, is going to cause an increase in the relative molecular mass, because colligative property is inversely proportional to relative molecular mass. Once colligative property is low, relative molecular mass is high, and once colligative property is high, relative molecular mass is low. They are inversely proportional. I'm saying that I've told you intermolecular hydrogen bonds form when you form hydrogen bonds between 2 molecules, 2 or more molecules. That's why we call them intermolecular. We are forming hydrogen bonds between 2 or more molecules. So if you look at this molecule of ethanoic acid alone, this is one molecule and this is the second molecule. So the bonds that we form between these molecules, between the oxygen and hydrogen atom, are going to be called the intermolecular hydrogen bonds. This one is an intermolecular hydrogen bond, and this one is an intermolecular hydrogen bond. Now you're saying that the relative molecular mass of sodium chloride obtained by boiling point elevation is going to be 29.25. Explain the reason why. The first thing first is to capture the actual molecular mass of sodium chloride. which is going to be 1 times 23 to get 23 plus 1 times 35.5 to get 58.8 as the molecular mass. So if you look at this, the actual value is twice the value which is given. And what did I talk about sodium chloride? Sodium chloride, first of all, is a non-volatile solid, and it's a strong electrolyte that undergoes full dissociation. So sodium chloride, 1 mole of sodium chloride dissociates to give 2 moles of sodium ion and chloride ions. So that means that one solid particle gives 2 solid particles in solution. What will that affect? How will that affect the value of colligative property? That's why we are saying that 1 mole of sodium chloride is going to form 2 moles of sodium ions in solution. And they are saying that since 2 moles of ions in solution, and they're saying that since boiling point elevation is a colligative property, which is directly proportional to the number of the solid particles present in that solution, the more the solid particles increase in the solution, the more we increase the value of colligative property. That's the meaning of that statement. So the more solid particles, the more sodium chloride undergoes dissociation, the more the boiling point elevation increases. And the more it increases, since I said it's inversely proportional to the relative molecular mass, the more the relative molecular mass lowers. So that's the logic behind it. So you're saying that since boiling point elevation is a colligative property, which is directly proportional to the number of solid particles in the solution, the ionization of sodium chloride increases the boiling point elevation, but it's going to reduce the relative molecular mass to half of the actual value. Look at the calculations involving elevation in boiling point composition. Now, if you look at the calculations, they are all going to involve the same formula, just like we described in the experiment. First of all, the solvent must be on the left-hand side and the solute must be this side. That's for the case of masses. And the other thing is, elevation in boiling point is going to be caused by the mass you have got. And then you proceed with the other calculations. So if you look at calculation number 1, they tell you that the solution is containing 60 grams of this, which is dissolved in 50 grams of water. Water is a solvent, so this is a solvent. This is going to be our solid. Now we are being prompted to calculate the boiling point of the solution containing. You are prompted to calculate the boiling point of the solution, and they told you that R is going to be equal to 43, hydrogen is equal to 1, carbon is 12, and oxygen is 16. And then the boiling point constant, or Ebullioscopy constant for water, is this. Now, since they want to calculate the boiling point of the solution, we have to first undergo different things so that we can get elevation in boiling point. Now, we say that 50 grams of water are going to dissolve this. Then what about 1,000? This should be your first step. Given mass of a solvent dissolves a given mass of a solid. What about 1,000? Dissolves what? This is the something you should start with. Now we have to get molecular mass of our solid. Molecular mass of our solid is this. Now the reason why we are getting molecular mass of our solid is because we were given Ebullioscopy constant, and I told you Ebullioscopy constant is always equivalent to always gives the relative molecular mass. So you're saying that this relative molecular mass was caused by the Ebullioscopy constant temperature, which is 0.54 degrees Celsius. But what about the given mass that we calculated? Because the given mass that we calculated is the one that is going to give us the elevation in the boiling point caused. So that's going to be equal to, so this mass here is going to give us the elevation in boiling point, but they want boiling point of the solution. And how do you get boiling point of the solution? We get it from the elevation of boiling point. And elevation of boiling point is got by boiling point of the solution less boiling point of the solvent. So we make the boiling point of the solution the subject by taking this one this side, and it's going to turn to a plus sign. So we're going to end up with 7.3636 plus 100, and we shall all end up with 107.36 degrees Celsius. Now if you go to part B, say the assumptions you have made. Assumptions can also be called limitations, and I've told you all these ones must remain the same. Now here, once a solid is specified, it's always advisable to specify that solid. You tell us that your solid, which is this one, should not undergo association or dissociation in the solution. You also tell us that the solution should always be dilute. Also, there should be no chemical reaction between the solid and the solvent. And lastly, your solute should be non-volatile. Here we are repeating the same concept that I explained earlier. We have been told the 2% aqueous solution of urea has a boiling point of this. Now you have been prompted to calculate the boiling point of pure water if its Ebullioscopy constant is given as 0.52 degrees Celsius per mole per kilogram. Now still, I've interpreted this for you. This means that we are having 2 grams of a solid that is present in 1,000 grams of a solution. That's always what 2% means. 2 grams of a solid are being dissolved in 100 grams of a solution. So to get mass of the solvent, you always have to get the 100 gram, you less the mass of the solid, which is 2 grams. So mass of water, which is our solvent, is going to be equal to 100 less 2 to give you 98 grams. So I've already told you this side mass of solvent, this side mass of solid. So 98 grams of water dissolves 2 grams of the solid, which is this. What about 1,000 grams? This one is always constant. So it's going to be 1,000 times 9 times 2 divided by 98, and you are going to get this. But remember that the mass you get here is caused by the elevation in boiling point. Now, how can we get elevation in boiling point? I've told you the mass you always get here is caused by elevation in boiling point, and if you look at your question, they told you to calculate the boiling point of pure water. Now that means that we don't have to deal with the boiling point elevation right now, but we are given the Ebullioscopy constant, and I told you Ebullioscopy constant is always equal for a solvent, is always equal to the relative molecular mass of the solid that is being given. So that's why we get the solid that is being given here. We calculate for its RFM, which is going to be given by this, and we are going to get 60 grams. The 60 grams is going to be contained by the Ebullioscopy constant that was given, which is 0.52. These ones are always equal. To get RFM of a solid, we must equate it to the Ebullioscopy constant of a solvent. As simple as that. Then what about the mass that we calculated? The mass that we calculated is always directly linked to the elevation in boiling point. So if 60 grams of a solid contain that, what about the mass of the solid that we calculated? Is going to contain which temperature, or is going to cause which elevation in boiling point? So you're going to find that it's going to cause an elevation of 0.1769 degrees Celsius. So that means that you're going to get an elevation in boiling point by elevation in boiling point given by boiling point of the solution less boiling point of the solvent. And then you make boiling point of the solvent the subject. So it's going to be solution minus the boiling point elevation. Now for the solution, it was given as 108, and then you less the boiling point elevation, which is 0.1769, and you're going to end up with 99.9 degrees Celsius. Question number 3. You are being told that 2 grams of phosphorus, that means that phosphorus is your solid, raise the boiling point of 37.4 grams of carbon disulfide. That means that carbon disulfide is your solvent. Now if you are to interpret that using colligative properties, we say that this gram of a solvent, which is carbon disulfide, is going to dissolve a given gram of a solid, which is 2 grams of phosphorus. Now the next step is always with 1,000. What about 1,000? It's going to be 1,000 multiplied by 2 divided by 37.4, and this is going to be grams of phosphorus. I've already told you that this one is directly linked to elevation in boiling point, and the Ebullioscopy constant always, when given, is linked to the molecular mass of the compound that is given. But here you are told that the 2 grams of phosphorus raise the boiling point of carbon disulfide by this. They use this word by. raises by. So that means that they gave us the elevation in boiling point when it's already calculated. And I've told you that the mass you have calculated is always given by the elevation in boiling point. So that means that this elevation in boiling point that was given is the elevation that is caused by this mass, which is 53.4759 grams. Then what about, now since we want molar mass, and molar mass is equivalent to the Ebullioscopic constant of the solvent used. If you're having this as your elevation, what about the Ebullioscopic constant? Whenever we calculate for Ebullioscopic constant, it's going to give us the relative molecular mass of that compound or solid that we are calculating for. So what about 2.35 degrees Celsius? It's going to be elevation in boiling point caused by 2.35 multiplied by 53.4759 and everything divided by 1.003. And we're going to end up with 125.29 grams. Now you're saying that the molar mass of phosphorus in carbon disulfide is therefore going to be 125.29 grams. Now if you go to part B, Roman number 1, they have told you to determine the phosphorus, the molecular formula of the phosphorus in carbon. Now you have been doing this ever since what level? We just attach N in bracket, and outside bracket we attach a formula inside. So it's going to be Pn. Pn should be equal to the molecular mass you have calculated, and phosphorus is equal to 31. So 31 times 1, then times N is going to give you 31N. You divide through by 31, you end up with your N being approximated to 4. So that means that phosphorus exists as tetraatomic. And we are going to conclude that the molecular formula of phosphorus, therefore, in carbon disulfide is going to be P4, which indicates that phosphorus is tetraatomic in nature. Solutions are always going to remain the same. The solution is dilute. No chemical reaction between the solid, which is phosphorus, and the solvent, which is carbon disulfide. The phosphorus should be non-volatile. And they're saying that therefore, Roman number 3, therefore phosphorus is going to exist as a tetraatomic molecules in carbon disulfide. So if you look at Roman number 4, 0.90 grams of a solvent was dissolved in 100 centimeters of cubed of benzene. Now here, I told you in the previous calculations, to get masses of any component, you get the given volume times the density. So how are we going to get mass of benzene? We get the density times the volume that is being given. Now in that case, you are going to end up with the density that was given is 0.879 times the volume that you are going to use, which is 100. And once you multiply that, you are going to end up with 87.9 grams as your mass of benzene. Now we're saying that that gram of benzene, this side we have solvent and this side we have solid. 87.9 grams of benzene dissolved 0.9 grams of the solid. Then what about 1,000? So it's going to be 1,000 multiplied by 0.9 divided by 87.9, and everything is going to give you 10.2389 grams of the solids. Now this is after calculating this is always equated to the elevation in boiling point. If you look at the question, they ask you to calculate for the relative molecular mass. Now here they tell you that the solution boiled at 0.25 degrees higher than the boiling point of benzene. So that means that this was already the boiling point elevation, and you need to be very keen when you're analyzing these questions. So boiling point elevation is always attached to this mass. So since they want molecular mass, we have to look for the mass that is contained in the Ebullioscopic constant, which was given as 2.52 degrees Celsius per mole per Kelvin. So 0.25 degrees Celsius is the elevation in boiling point caused by 10.2389 grams of a solid. Then what about 2.52 degrees Celsius? This is going to be the elevation in boiling point caused by 2.52 divided by 10.2389, everything divided by 0.25, and you're going to end up with 103.21 grams. So the relative molecular mass of the solid is therefore going to be 103.21. Number three, they told you that the boiling point of pure water is 100 degrees Celsius, but when 1.97 grams of potassium chloride were dissolved in 125 grams of water, the solution boiled at a relatively higher temperature of 100.11 degrees Celsius at a pressure of 760 millimeters of mercury. Explain this observation. And part B, from the information given in part A above, calculate for the boiling point constant, provided the molar mass for potassium is 39.1 and molar mass for chlorine is 35.4. Now here for part A, it's about explaining the value of colligative properties. And as I've told you, you have to first start by saying how the solute you are dealing with is non-volatile. After saying that, that means that some of its particles are going to occupy part of the surface of that solution. When they occupy part of the surface of that solution, it will inhibit or reduce the escaping tendency of the liquid molecules into vapor phase. And once that happens, our solution is therefore going to have a lower vapor pressure than that would be exerted by pure water. Now you're saying that the solution should therefore be heated at a higher temperature than the actual boiling point of pure water, so that the its vapor pressure gets in equilibrium with the atmospheric pressure for boiling to take place. Now if you look at part B, mass of the solvent was 125 and its dissolving mass of the solid is 1.97 grams. What about 1000? The mass you always get is directly linked to the elevation in boiling point. So what's the elevation in boiling point? You get this one, which is 100.11. You less the pure solvent, and elevation in boiling point is thus going to be 0.11 degrees Celsius. So this elevation in boiling point is what caused this mass. Then what about, now since they're asking for boiling point constant, so that means that this mass caused this. Then what about the RFM of potassium chloride? So that means that we have to go ahead and we find the RFM of potassium chloride. Potassium chloride is given by 1 times 39.1. Always use the molar mass that have been specified in the question because they want to reduce specific errors. Now a student who doesn't use the mass as given in the question will always get the answers wrong because you didn't follow instructions. So this 74.5 gram is always equal or equivalent to the Ebullioscopy constant. So that if the mass we calculated above is equivalent to the elevation boiling point, then what about this mass? This mass is going to give us the Ebullioscopy constant. That's why you're saying that 15.76 grams of potassium chloride elevate boiling point by 0.11 degrees Celsius. Then what about 74.5 grams of potassium chloride? This is going to elevate the boiling point by 74.5 multiplied by 0.11 and everything divided by 15.76, and it's going to give you 0.52 degrees Celsius per mole per kilogram. And you're saying that the boiling point constant of water is therefore going to be 0.52 degrees Celsius per mole per kilogram. Now if you look at number 4, define the term boiling point elevation constant of a substance, which you have already defined. And part B, you are being told that the boiling point of benzene under a certain pressure condition is 80.0 degrees Celsius. And calculate the boiling point elevation constant of benzene if a solution containing 5 grams of 2,4,6-nitrophenol in 100 grams of benzene boils at this temperature. So first of all, we start with solvent dissolving which grams of a solid. So we are given 100 grams of benzene dissolving 5 grams of 2,4,6-nitrophenol. Then what about 1000? And the answer you get, this mass you always equate it to the elevation boiling point. Now what's going to be our elevation boiling point? The solution boils at this, and the solvent boils at this. So to get elevation boiling point, we get that one, boiling point of the solution, and release boiling point of the solvent, which is going to be 80.568 less 80. So that you end up with 0.568 degrees Celsius. Now here, molar mass therefore you are going to end up with, you have to calculate, since they want they are telling you to calculate for the boiling point elevation constant or the Ebullioscopy constant. You have to find molar mass too. And I've already told you how we find molar mass. You have to show this, and you end up with this in total. Now, since the mass we calculated is equivalent to the boiling point elevation, then what about the RFM of it, which is going to give us the Ebullioscopy constant? So 50 grams of the solid elevate the boiling point by 0.568 degrees Celsius. Then what about the RFM, which is always going to give us the one for the Ebullioscopy constant? It's going to elevate by what? 9 grams of the solid is going to elevate our boiling point by, is going to be 229 times 0.568 divided by 50, which is going to give you 5.6 degrees Celsius per mole per kilogram. And the boiling point constant of benzene is thus going to be 2.6 degrees Celsius per mole per kilogram. Now if you look at number 5, calculate the mass of sucrose that would have to dissolve in 1000 grams of water so that it can raise the boiling point of 101.7 degrees Celsius, provided the Ebullioscopy constant for water is 0.52 degrees Celsius per mole per kilogram. You're seeing that the elevation boiling point is going to be given by this, which is going to be equal to 101.7 less 100 to get 1.7 degrees Celsius. And molar mass of sucrose is going to be given by this. You have to show how you are multiplying because it carries a mark. So once you use the calculator, you are going to end up with 342 grams. Now you're saying that 0.52 is going to be the elevation boiling point caused by this. Then what about 1.76? Because we are looking for the mass of the sucrose or the RFM. So what about 1.7 is going to be the elevation boiling point that is going to be caused. Now we are here in this case. The Ebullioscopy constant, we attach it to the RFM. Then the elevation boiling point is going to be to give us the mass that was required or that was used for this experiment. So that means that 1.7 degrees Celsius, the elevation boiling point caused by 1.7 multiplied by 342 divided by 0.52, and everything is going to give you 1118.08 grams. And therefore the mass of the solid required is going to be 1118.08 grams as required. The graphical representation of the boiling point elevation. Now we are saying that a graph of boiling point elevation against concentration can be plotted as follows. Now it's going to be elevation in boiling point against concentration. Now a graph of boiling point elevation against concentration of a solid in a solvent is always going to be a straight line passing through the origin. Now you're always going to get scattered points, but you're always supposed to do the line of base fit. The line of base fit, you're always going to find that it's going to be a straight line passing through the origin. Now you're either going to be asked for the Ebullioscopy constant or the molecular mass. So you're saying that you're going to be using this formula for finding, to help you find either the Ebullioscopy constant or the molecular mass for any solvent or solid being asked for. Now you're saying that the solid of the graph, the slope of the graph is going to be equal to Kb divided by the molecular mass. Now we're saying that if Kb of the solvent is known, the reactive molecular mass of the solid can therefore be calculated. And the data you are usually given may require you to find or to calculate the elevation in boiling point first before the graph is being plotted. That brings us to the end of this video. Now we shall be meeting the other video to proceed and to finish up with colligative properties, and we are going to be looking at depression of freezing point and osmotic pressure of the solution. Now share the video to your friends and discuss so that you can all benefit as a family.